In this part of the session, we'll learn about value additions due to additive manufacturing. We'll learn why should one use additive manufacturing for making the whole component or a small part of it. We now already know the whole detailed history of additive manufacturing. Let us see what benefits additive manufacturing has over the conventional processes. Additive manufacturing offers improved functional performance. For example, if you want to make a part which needs to have various properties at various locations of the parts, that can be imparted using additive manufacturing because we can create complex geometries using different materials. Additive manufacturing offers customization. Since it is based on design file that we create before starting the manufacturing, we can create a design based on individual preferences and choices of applications. Additive manufacturing also offers complex geometry and topology. Due to creation of complex geometries and topologies, we can also impart less weight in the design by creating graded complex geometry throughout the section. We can create other forms of topologies. Instead of creating separate parts of small sizes of various materials, we can create a monolith structure using additive manufacturing in which different small sections or subparts are made using different materials, may have different topologies and different internal structures. We do not need to join small parts so that we can avoid now joints or welded parts in the large structures. Some of the materials are difficult to be made or use in the conventional processes. Some metals are very difficult to deform, some metals are difficult to melt, some metals are difficult to be stretched and so on. Since additive manufacturing offers local melting using laser or otherwise, we can avoid the workability issues of various materials. Additive manufacturing offers as needed manufacturing of really complex geometries and components. Thus, it also solves a very large issue in manufacturing which is called supply chain issue. We can make parts as needed. We do not need to have large inventory of raw materials and of the finally made parts. We do not need to create individual components of very large machine as mentioned earlier. Thus, just a monolith structure can be created and can be used immediately. As we now know already, additive manufacturing is based on CAD files or design. We do not need dies, tools and other large structures, for example, foundries and mills. This is a toolless production process, and thus we can make small batches or large batches of the parts that we need. Because of this new methodology of design, we can make faster design and we can make small changes iteratively in the part that we want to make more quickly. It offers faster design iterations. We do not need to change dies, mills, forging assemblies every time we want to make a new part. Thus, the whole process is very cost effective. All we need to change is the design CAD file. Additive manufacturing offers flexible production. That means we can make the part where we need it. We can make small section of a large part. We can make it on any given substrate and so on. It also offers reduction in design to proof of concept. That means very first time when you have created a design and you want to make a part, it takes very small time to create the first instance of the part that you want to make. All we need to do, as we mentioned in the first session, that you need to create a file, you need to choose which material you need, and you need to think about the application so that we can choose various process parameters. Sometimes we use machines and structures that are now very old and the parent company or the manufacturer is not offering that anymore. It is very easy to manufacture such parts using additive manufacturing, because all we need to do is we need to scan these geometries and create a topology that we need, choose the material and print it using additive manufacturing. Additive manufacturing also offers fast ground maintenance and repair and overhaul, and that is because if small sections of a large part are broken, we can bring the additive manufacturing assembly near that large machine and can print only that missing part or the broken part very quickly. We'll go through some examples in detail. Here is a very complicated part of an aircraft engine in which the outer casing is made of a complex topology which is also called lattice structure. This type of lattice structure offers weight reduction. This assembly is also connected to a fuel channel which, using conventional process, was supposed to be produced separately and added to this casing of the engine. However, as mentioned earlier, using additive manufacturing, we can create this whole geometry as a monolith structure. Apart from the fuel channel and the casing, this structure has many other complicated parts as seen in the top part of the geometry. There are various smaller channels, there are more complicated topology and structures which all can be printed using additive manufacturing. Also, we can create a graded lattice structure as seen in the second figure. We can have finer lattice structure at the surface, we can have more coarse structure at the inner section of the geometry. We can have the thickness varying as per the need in different sections of the geometry. A more close-up figure of this structure is shown in the third figure. Overall, additive manufacturing offers improved functional performance because we can create the geometries in various parts of the large structure as needed. For example, this fuel channel and the smaller channels in the other part of this large engine casing. We can have finer control when we are creating complicated geometries and lattice structures using additive manufacturing. So, it offers superior topology in complex geometry. Additive manufacturing, now as we are clear, offers monolith design which avoids joints in the large structure, corrosion and so on. Due to these microstructures, micro lattices and complex topology, the weight of this overall structure is much less as compared to a solid structures where the walls are made of solid material. The structure so made is energy efficient, it uses less fuel, it is lightweight, it offers functional performance in various zones. Wherever we want better fluid flow, it offers that. Where it needs less heat extraction, it offers that as well. Overall, it is a monolith structure. This example shows that AM offers flexibility to manufacture complex shapes. It offers application of various materials in various parts of a large structure. It offers complex topologies and geometries. Overall, we have a more efficient and lightweight engine casing. Here is an example of customization and individualization. Teeth crowns are used when teeth surfaces are not intact, they are deteriorated and there are issues, for example, in chewing. Zirconia is one of the materials which is used for making teeth crowns. These materials are hard Additive manufacturing, since it is based on designing, offers individualization of making such teeth crowns. The ear openings of individual humans are different, and once we have captured the geometry, we can create various types of earplugs based on individual needs. Thus, additive manufacturing offers something that conventional processes do not. Conventional processes need sophisticated custom toolings and fixtures which are difficult to make and they are expensive. They are made of very sophisticated materials, and based on the individual designs, the tooling change is not very feasible. The quality of the final product is also heavily dependent on what type of toolings and dies are used. AM avoids material workability issues because it can use the materials which are difficult to shape or melt otherwise. It offers customization and individualization because products can be made based on individual designs. It is a toolless production process, thus quick batches can be produced based on the design files. If we look at the cost of additive manufacturing versus conventional process, additive manufacturing offers a much cheaper option when we have to create smaller lot sizes of even complex parts. If we want to use conventional processes for smaller batch sizes, we need to create tools and assemblies, dies, etc., which are made of very expensive materials. Additive manufacturing, since it is based on individual designs, the process is not very expensive even for small lot size, and the cost does not change much if you increase the lot size. This example shows how additive manufacturing gets rid of supply chain issues and offers quicker iterations in improvement of design. As we know, for additive manufacturing, we need a CAD model. We create STL file. This STL file can be used for creating various slices of the final geometry using G-code generator. This final file is sent to a printer communication drive which is connected to a controller firmware, and we can choose the process as we need. We can make the part, if suitable, using powder bed fusion or photopolymerization or binder jetting, material extrusion, or direct energy deposition or sheet lamination. Because of so many options available, additive manufacturing offers cost-effective iterations. If we do not like a part or it is not performing based on the theory or the design that we used, we can go back and change the design and can print it again using a different process this time, can measure the properties. If again the properties are not as expected, we can again change the file or simply can use a different process this time. It also gets rid of supply chain issues because we need only the raw material which is needed for making that particular part. We do not need to have a large inventory of the finally made parts. As soon as we make parts, we can supply them to the end user. We can do faster design iterations as explained earlier. Additive manufacturing also offers flexible production because raw material, the design, or the method of printing can be changed very quickly as we need them. We can also print the part where it is needed. That means the locations which are not easily accessible can have access to the additive manufacturing facility and the part can be made at that location itself. Overall, as we have learnt now, additive manufacturing also offers short time to prove the design concept. Additive manufacturing offers reverse manufacturing of obsolete or legacy parts which are now out of production. We do not need to have blueprints of these parts. We can simply scan the geometries and create CAD files and print them. Of course, some planning of material and the applications is needed. It also offers fast ground maintenance, repair and overhaul. We do not need to have large inventory of material because if we want to simply repair, we need smaller amount of materials. We do not need to even disassemble the whole large machinery. We do not need to print the complete part again. This is a huge cost saving since small amount of material and time is being used. We can also make the additive manufacturing assembly available where the locations are difficult. Some examples are shown here. For example, if some part of this gear which is shown here is broken, we can print only that part of the gear right on top of the base material. Some more complicated geometries are shown which can be in full or in parts can be printed using additive manufacturing. In this particular example, figure E, two different materials have been used and such assemblies are very easy to be printed using additive manufacturing. In the bottom figure, a broken turbine blade is shown. Using conventional process, we will need to make the complete assembly of this blade, which is expensive and time consuming. Using additive manufacturing, we can print only this missing part or the broken part on top of this matrix. Some preparation may be needed on the surface, however, still the time taken and the material taken to repair this broken blade is much cheaper as compared to the conventional process. We'll meet in the next session. Thank you for listening.